Path of a reaction and the effect of a catalyst. So the equilibrium constant tells us how far the reaction goes. Does it go all the way to the products? Does it hardly make any products? But the rate, the reaction rate, tells us how fast it gets there. So equilibrium constant tells us position, the rate tells us the speed. There is an activation energy, or it might be easier to think of as an activation barrier for reactions. And that's the energy barrier that has to be overcome in order for the reactants to be converted into products. For most chemical reactions, this has to do with there are chemical bonds that have to be broken before you can make new compounds. Before you can take that Lego structure and make it into something else, you have to take it apart, and that takes energy. So you have to break the existing bonds before you can form the new bonds. So in general, at a given temperature, the higher the activation energy, the slower the chemical rate. We talked about collision theory, right? And so in order for this reaction to occur, the hydrogens and the oxygen have to run into each other, and they have to have a collision with enough energy to produce a reaction. If they just barely bump into each other, nothing's going to happen. They have to collide with enough energy that they get over this barrier. In order for these to combine to make two water molecules, we have to break two hydrogen-hydrogen bonds and one oxygen-oxygen bond. And that's going to be broken by that energy of collision, these things ramming into each other. Chemical reactions are really very violent if you go on down to the particulate level. So if this barrier is high, it's going to take more energy to get over. And so fewer collisions are going to have enough energy, and the reaction will be slower. If this barrier is very low, more collisions are going to have enough energy, and so the reaction will proceed faster. So higher activation energy generally means a slower reaction rate. When I look at these diagrams, it reminds me of playing miniature golf. So in miniature golf, there's all these little humps and speed bumps and stuff on the little putting greens, right? And so to get your little golf ball over and down to where the hole is, you have to hit it with enough energy to get it over. The higher the hump, the more energy you have to hit it with. If you don't hit it hard enough, it just rolls back to you and no reaction occurs. And that's a lot like how chemicals react. Well, if we have a slow reaction, is there anything we can do to make it happen faster? We're very impatient, right? And we want to make things happen faster. And sometimes it's not just us being impatient. There's valid reasons for that. Well, there's a couple of things that can be done. You can increase the concentrations of the reactants, because if you have a higher concentration of reactants, you're going to have more collisions, right? We talked about kindergartners in a room. And if you have, 100 kindergartners in this room and they're running around, they're going to bump into each other a lot. If the concentration is lower, maybe there's only 5 kindergartners in here, they're not going to bump into each other as much. More frequent collisions means faster reaction. The other thing we can do is we can increase the temperature. Increasing the temperature causes the particles to move faster. And that does two things. It increases the number of collisions. They're going to run into each other more often. And because they're moving faster, those collisions have higher energy, so they're more likely to produce a reaction. Sometimes those options are just not possible, and so there's another way, and we can use a catalyst. And a catalyst functions, thank you, Train, by lowering the activation energy barrier. So here we have an illustration of pushing rocks off a cliff. So here's some boulders, and to push them off the cliff, we have to first get them up this little incline here to this point, and then give them just a little tiny nudge and they'll go over. But we have to expend energy to push them up the hill. So what a catalyst does is it offers a different pathway. It says, well, oh, I didn't mean to do that. There we go. I don't know why I like green. Instead of going up and over that hill, why not go around the hill? You don't have to push them nearly as high. Let's go around the hill, and that's a lot easier. So if you were pushing boulders off the hill, it would take you a lot longer if you had to go up and over this hill. Catalyst gives you an alternate pathway. So that's what a catalyst does for a chemical reaction. It gives an alternate pathway that has a lower activation energy. So now if you imagine somebody standing here hitting golf balls. So here's somebody playing miniature golf. And there's the ball. So they're going to hit the golf ball, and they have to get it over this big hump. Well, many times they're not going to succeed because that hill is so big, right? If we cut the hill down, if we make the hill lower, now this person can hit golf balls over that little hump much faster. Does that make sense? So it provides an alternate pathway that has a lower activation energy. Enzymes are biological catalysts. So if you may not have thought about this, but your body is like a chemical factory. Your life is possible because of gazillions of chemical reactions that are occurring. And those chemical reactions, their rates are dependent on temperature and concentration. And some of those reactions occur very, very slowly. But you can't just increase the temperature of your body because some of these are thermally sensitive. And if you increase the temperature too high, the molecules combust or fall apart. And so your body has a regulated temperature. We also can't just increase the concentrations. That's not always possible. Your body can't just suddenly make more, and why would it do that? What your body does to control its chemical reactions is use enzymes. And the enzymes are catalysts. So the basic way an enzyme works is that, here we're going to use this example of sucrose, which is a disaccharide. It's got two sugars bonded together. And when your body metabolizes sucrose, that's table sugar, it breaks it apart into glucose and fructose. Well, in order to do that, there's a high activation energy, and the reaction is too slow to be useful for your body. So your body uses an enzyme called sucrase, which catalyzes the hydrolyzation of sucrose, makes it a lower energy to do so, and so it speeds up the reaction. The way it does that is, here's the molecule sucrase, just a globby picture of it. What it does is it has an active site, and so it's kind of like a landing pad, or sometimes we use a lock and key analogy. So the sucrose is like a key that fits into this lock, and not just any key will fit in, only certain keys, sometimes only one particular key. And so the sucrose fits into this hole, this active site on the sucrase. And when it fits in there, tension is put on this bond that holds those two sugar particles together, the different saccharides. And that weakens that bond. So now it's much easier to break that bond and end up with the glucose and the fructose. Any questions about that? So studying chemical reactions like this is called biochemistry, and it's a pretty fascinating area to study.